One of the biggest questions I get from students when it comes to tensile tests and engineering stress strain curves is why is my elastic modulus or Young's modulus so low? So in this video, we're going to try to figure out what could cause this. So to do this, we're going to look at three things. The first one, we want to make sure we double check our results. I know we're all good engineers and scientists, but double check your results. That means calculations, equations, all of that. Also, with that, units. Make sure you check your units. This is a big one. This is probably the number one thing that happens if you haven't carefully double or triple checked your results. Next, what is your expected value, right? So if you're saying your elastic modulus is too low, that means you have an expectation for what it is. So let's check those values and the units as well. And lastly, the last thing that I typically go through and check is what is the experimental setup. So whether this is a tensile test that you've run or somebody else, or maybe if this is a problem that you're going through, you want to make sure you know what the experimental setup is. So let's go and look at each one of these individually. And let's start with the calculations. So again, you want to make sure you double check your work and particularly pay attention to the units. So let's go through the calculations that you'll have to do to get to the elastic modulus. And so the raw data that we get from tensile testers is going to give you displacement, force, and then we calculate everything from there. So the first thing we need to calculate is engineering strain, and that's what I'm showing here. So engineering strain epsilon is equal to the displacement, so delta L, or the difference in length, over the original gauge length. So both of these units are going to be in either millimeters or inches, and so this will be unitless, sometimes given as millimeters over millimeters or inches over inches, but it is, in fact, unitless. Next, we'll have to calculate engineering stress, or sigma. So sigma is force or load divided by the original cross-sectional area, A naught. So the force or load is given to you by the software. And then we typically have to calculate the cross-sectional area based on the dimensions of our tensile dog bone. So that's the two things that we need to calculate and to plot an engineering stress strain curve. And lastly, we can get to the elastic or Young's modulus, E. So this is the engineering stress divided by the engineering strain, or sigma, over epsilon. And therefore, this is going to be a slope. And particularly, this is referring to the slope of the linear elastic region of our curve. And so because of the units of sigma being, in this case, Pascal or megapascal or gigapascal, then this is going to have the same units because epsilon or strain is unitless. And so it's either going to be something like gigapascal or PSI or KSI in imperial units. So those are the calculations we'll want to double and triple check. And again, you'll see a lot of units here, and you want to make sure that you have a good grasp on that. Make sure you double check everything in your spreadsheet or so forth. So next, we think our value is low. So we want to make sure that we have an accurate idea of what that value should be. So I've got some values here for different types of materials. So number one, metals. This is a lot of what you might be tensile testing on. This is very common. And so we can have a range of values all the way at the lower end of 45 gigapascals for magnesium alloys up to 400 gigapascals for tungsten. So that's a range of 6,500 to 58,000 KSI, again, imperial units. If instead you are looking at a polymer, that could range all the way from a very low 2 megapascal for elastomers up to 5,000 megapascals for phenolics and other types of stronger polymers. So this is a range of roughly 290 psi up to 725 ksi. So again, a very wide range. So make sure you know as specific as possible what your material is. And lastly, I put a very specific example here because this is the one that I'm going to go through here in this video. And that is a alloy called 4140 steel. This material specifically has an elastic or Young's modulus of 207 gigapascals, which translates to 30,000 ksi. So all of these values are from the Fundamentals of MSE by Callister, the 6th edition, if you're curious. So look in the back of your book, your textbook, if you're using an intro to MSE type book. They're going to have a lot of useful values here. If you look online, just make sure you have a reputable source that you can find the original information for those values for. All right, so that's number 2. So 3, the setup. I mentioned what is your setup. So if you've collected this information, you'll know what this is. If somebody else did it for you, see if you can ask or see if you have this information, or if it's a book problem, it might take a little bit more to try to figure this out. But the setup. So if you've done this test, you'll kind of recognize over here on the right, this is a tensile tester or universal mechanical testing frame. That's what we use to test and do a tensile test. So the components here, the big pieces here, the big kind of circular pieces are the grips for holding our sample. They are connected to the load cell here, which is connected to this crosshead here. The crosshead, in this case, moves up in the upward direction during a tensile test, which is driven by either screws or hydraulics that are built into the columns on the sides. So the bottom is fixed, and then the top, which is connected to the crosshead, moves up. And so that's how this test works. So the grips attached to the grip sections you can see here on the diagram of our tensile dog bone. And again, we would be putting this up vertically instead of horizontally like it's shown here. But these are attached to the grips, and then this is pulled in tension until it fractures. So that's our setup. That's the overall geometry of our sample. And so we'll note a couple things. The grips, these are wide for holding in the machine. And then it reduces to a reduced section here. This is where the stress is going to concentrate, and this is the portion of the material we're sort of focusing on because the stress is the highest, and so that's the part where we're essentially testing, and everything else is set up in order to hold that sample there. So we can get the diameter or the width depending on the cross section. We have a reduced section, and importantly, we have something called the gauge length. So this is the initial length that we're going to talk about in this case. All right, so this, if you recognize these parts from the test that you've conducted, great. And so as far as the setup, there's one final question. So what did you use to measure the displacement or the extension? So in this setup that you see here, displacement or extension, so how far this is being pulled at any given time, is measured by the crosshead. So the crosshead can move upward, and as it moves upward, its distance, its elongation is being recorded. And so that is one way to measure the displacement or the change in length in the sample. The other way to do this is with what's called an extensometer or an extensometer, however you want to pronounce that. Both are fine. But these devices measure the displacement and specifically do it on or between the gauge length. So instead of measuring the displacement of everything in the machine, we're only measuring the displacement between the gauge length on the reduced section. So here you can see we have two forms of this. We have general classes of extensometers. We have a contact type. This is personally what I've used on machines that I've operated, where we have a device that attaches, and you can see these clamps or kind of clips here attach, and they're going to attach right on the gauge length. and then this device tries to stay on that length, and it moves with the sample. So when the sample extends, so does this arm and this arm as well. And so then the device measures that extension, but again, only between that distance. So if this is a 1-inch gauge length, it'll start out at 1 inch, and then as it moves, it will go 1 inch plus whatever the displacement is. So this is a contact version because it's making contact with the sample here. The other form, which is quite possible that your device has, is a non-contact extensometer. These are becoming more and more popular. They're a little bit more expensive, but they work very well if you have them. And so you'll see the grips, they're big in this case, and you'll see the sample hopefully here, and you might notice the 2 dots. Those 2 dots, again, represent the gauge length, and they're typically painted or drawn on our sample with some type of pen or marker. And what happens is those marks are the gauge length of the initial bar. And as the sample goes up, right, and it's going to extend, that distance between the dots is measured with some type of optical or camera system like you can see over here on the left. And so it does by non-contact, by digital images, and so this is a non-contact. So there's different versions of the non-contact, there's different versions of the contact, but that's the 2 main approaches. You can also use a strain gauge, but strain gauges usually require a lot of prep and careful know-how, so they're not as common as an extensometer for routine tensile test. So this is typically the way that we're going to record it. And so again, when we ask the question about experimental setup, the question will be, did you or did you not use an extensometer? Because again, that strain from the displacement that we measure will be different, whether we're recording it only from the gauge length or whether we're measuring it from the entire device. And so without the extensometer, when we measure that displacement, again, it's from the crosshead movement. So this crosshead will move up and its position is monitored. And so that displacement is monitored. So what happens is the extension or displacement in all parts of the system are collectively measured. So inside the gauge, but also this region out here outside the gauge length is also extending. The grips can extend. The grip itself can move. There can also be extension in the any sort of junction that we have. So typically the grips are attached to the base here by junctions up here to the load cell and so forth. So all of that stuff can get displaced. And so that's all collectively adding to a displacement, meaning that the strain is also going up. So that strain is going to be bigger than the extension strain. All right, so with that kind of basic overview, I wanted to go through an example with 4140 steel so that we can take a look at these 3 points. So again, double checking our results, we can look at expected values, and then finally, we can see if anything about the setup is causing this. All right, so we're here in a simple Excel spreadsheet having our data that was done for a 4140 steel alloy. We've done a tensile test. This was done with an extensometer, and so we'll get to the different parts here. We recorded the thickness and width. So since we have a thickness and a width, this means it's a rectangular cross section, and we also recorded the gauge length. So all 3 of those are manually done with calipers. And then what our machine and software and program spit out was time. So it's always good to have time measurements. Displacement. So again, that's how far we have in movement. Force. Tensile strain. Strain 1. And those are the categories that it spit out. Right. The rest of it was calculated beforehand, but I'll walk you through what we have. So we wanted to calculate stress and strain. So we're going to kind of go through and check these calculations. So this is our step one. So let's go to this first strain. So again, if we want to get the strain from the crosshead, the engineering strain from the crosshead, how we're going to calculate this. So if I click on this, you can see that it's got C7, so this one. So it's the displacement divided by B3, so the gauge length. So essentially the change in length at any given time point divided by the original gauge length. And so that's what I've calculated. And I've got the dollar signs there so that gauge length doesn't change. The original is always the same, but the displacement is going to change as I go to the different time points. So what that means is that the displacement, this displacement column, is from the crosshead motion, so not the extensometer. So this is common in the instrons that we have access to. I can't verify this is going to be for all instruments or all softwares, but this displacement category is for the crosshead. All right. So if we want to measure the extensometer engineering strain, that's what I have here. What we can do, and what you'll see the software, or what I have the calculation as, is this category, E7, which is the tensile strain, strain 1, and it's in a percent. So this is actually already calculated as a strain. That's how these devices tend to work. It's put it in a percentage, and so to be consistent, I'm going to remove that, which is why we've divided by 100. But pretty much that category is the engineering strain for the extensometer. So this is essentially the what we have. So I didn't have to do much other than divide by 100. So I've already got the strains, and I have millimeters over millimeters, but again, that's unitless. And the last thing is the stress. So the engineering stress strain. The engineering stress. So let's look at that one. So this one, again, units are always important, and so it looks a little crazy, so I'll walk you through it. So we're using D7, which is over here, and that's the force. You'll note from the software, we got kilonewtons. So because that's a kilonewton, I multiplied by 100 to make that a newton. So we have essentially force in newtons here, D7 multiplied by 1,000, and then divided by the original cross-sectional area. So that's where I have B1 and B2. So the thickness multiplied by the width. So that's our cross-sectional rectangular area. And so because both of those are millimeters, this is going to be millimeters squared. So what we have is a newton over a millimeter squared for this. And so this is where units are important, right? So if you had chose to do this in all kind of base SI units, you would have wanted to convert the millimeters to meters, right? So you have meter squared. However, I left it in millimeters because there's a handy trick in tensile test that a newton divided by a millimeter squared happens to be a megapascal or MPa. So that's always a good one to remember. But if you don't, just stick with the base SI units and then convert from a Pascal to a megapascal. So I've got that here. I would always recommend you check that yourself. Make sure you have the conversions and so forth. All right. So now we have the strains from both devices and the stress. So this allows us to test the difference and to see if this might look like what's happening for your sample. So over here, I've already plotted this. And so we'll demagnify a little bit so you can see it all. So this is our engineering stress strain, right? So on the x-axis, we have engineering strain, and again, millimeters over millimeters, and engineering stress, and then we have this in megapascals. So the blue curve that you see is the crosshead, and the red that you see is from the extensometer, but they're both engineering stress strain curves. A couple other things to go through that you might have picked up on. There's a little blip here, a little dip that kind of goes back. So this is just a minor blip in the system because our software prompts us to remove the extensometer that we're using And so what it does is it momentarily stops the test so that we can open the safety shield and remove the extensometer. And so when you restart it, it kind of goes back up. But we have this little hiccup if you're wondering where that comes from. The other big observation that you might notice is that they're quite a bit different. So the overall stress level is the same, right? So the top of the red curve is the top of the blue curve because that didn't change. But the strain did because I used two different strains. And so you can notice that the crosshead goes almost to 0.16 engineering strain, whereas the extensometer only went to about 0.1. So that's a pretty drastic difference because, again, all of that other stretching that's happening in the machine is being added up. And so that's what we're seeing here. So that's the big difference. And since we know that the elastic modulus is the slope of the elastic region, so this and this, we can see a drastic difference, right? So with the crosshead, we actually have a very low or relatively low slope here compared to this really steep high value for the slope. So even without the calculation, we can see that there's a difference here. And in fact, with the crosshead, we even get sort of two slopes, the initial region, and then it looks like it changes around here and has another slope. So I'm not exactly sure what that is, but when you use the crosshead, things like this can happen. So we can definitely see that in this case, if we were to just plot the crosshead, we could account, and we know this is maybe why our elastic modulus is so low. So let's get a little bit more into the details so we can, again, compare to the expected values. So if I scroll down here to my second plot, I've just taken the linear elastic regions. So again, the red curve and the blue curve. So this is engineering stress strain, just the linear portions. So I have those, and I have linear fits that we'll talk about here in a second. One other note I want to make, you saw that we had two slopes on the blue. I decided to just go with this higher initial slope region and kind of ignore the other slope. So that's kind of an assumption I made in this case. So after I've done that and isolated just those regions, I had Excel do a linear regression, a linear fit. And so I plotted and I showed the formulas. So that's what you see here. And then I also put an R-squared value so you can see how good the fit is. And you might even notice that the gray lines are the linear fit. So the fits are pretty good. You got 0.9991, 0.9938. So they're both pretty good. And the key characteristic that we want to look at, because we're interested in the slope, because that is the elastic modulus, is this number up here in front of the x. So for the extensometer, we have 204,692. Again, the units are going to be megapascal over nothing, so just megapascal. So this is the slope in megapascals. And for the crosshead, we have 34,427 for the slope. And again, in megapascals. So I've actually written them over here. So you can see, starting with extensometer, this is the slope that I just read off in megapascals. So if I divide by 1,000, which is what I've done here, you see that my slope for the extensometer is 204.692. So essentially 205. And then for the crosshead, that 34427 is in megapascals. Divide by 1,000 to get gigapascals. And the reason I'm doing this, the converting to gigapascals, is because if we remember, our expected value for 4140 steel was an elastic modulus of 207 gigapascals. So that's why I'm doing the conversion. So for the crosshead, you see that 34 gigapascals is nowhere near 207. In fact, it's close to an order of magnitude lower than our expected value. So again, this might be the value that you got when you personally did this and decided, why is my value so low? However, if you look at the data with the extensometer, so either if you have access to it and you forgot to use it, or maybe you don't have access to it, this is the value you would get with the extensometer. So it's basically 205. So 205 is not exactly 207, but this is very close to the expected value for 4140. So this is really in good agreement within the margin of error, I would say, for the fit and everything else that you're doing for this test. So again, if you're hopefully what this is showing you is that with or without extensometer is one of the big reasons we can get drastic differences in the extensometer. If you've looked at everything else, if you're good with your units, if all your equations look correct, if you've plotted everything, if you've done your linear regressions fine, then the difference in your setup between having an extensometer and not having an extensometer might be that difference between 205 compared to 207 or 34 compared to 207. So again, ask yourself when you're looking at these types of problems and you're seeing this drastic difference, check everything, check your units, check your expected value, make sure you're getting this from a reputable source, and then see if you used an extensometer or if you forgot to plot that data and see if that makes a difference.